Welcome to the episode 3 of the MiSTer Retro Wolf Guide to Simple Arcade Core Creation. In this episode we'll continue looking at the timing circuit that we started last time. We'll be looking at the waveforms from the breadboard and recreating it in Verilog using the Modelsim software. Let's get started. So here's our breadboard circuit we saw last time. I'm using the same logic analyzer we used before, but this time I've put the probes onto the NT, which is the 1H input into the 6B chip, the first LS161. The next four are the outputs of 6B, which are 2H, 4H, 6H and 16H. Then on chip 6C I've connected the probes to the output of 32H, 64H, 128H and the 256H- or not 256H. Finally, I've connected both the grounds to this wire that I use for the other logic probe. I'm back in the Csync software and I'll choose 9 channels to log. Okay, so it's logged info from the horizontal timing counters. It's looking okay, but I think there's a few things wrong. These ones are okay, but the channel 4 and 5 are in the wrong order. Probably hooked up the wires in the wrong order. Also, you can see that channel 7 and 8 are not what they should be. I'll take a look at that back on the breadboard. If I disconnect those two probes and reconnect them to get a better signal. Okay, now if I resample, then we get a much better result on those two channels. You can see overall that the frequency starts at 3 MHz and keeps halving down to around 15 kHz, which of course is the refresh rate of the horizontal component of the arcade signal. You can see we still have a few blips of weirdness on channels 4 and 7. If we refresh, you can see it's pretty much still there. So I moved the ground to the ground pin of an IC instead of a wire. After resampling with that change, you can see that the traces are better now with no blips. So for reference, we can check out our frequencies again. For the vertical timers, we have the chips 5E, 6E and 6D, and I've connected up the logic analyzer to again NT, which is V1, connected the two grounds, and then we have V2, V4, V8, V16, V32, V64, V128 and then V-Sync. Okay, so I've gone ahead and updated the logic data. So we can see that our traces are 8 kHz, 4 kHz, 2 kHz, 1 kHz, with an interesting additional feature. You can see here that channels 3, 4 and 5 have this additional increased period every 8 cycles. That's probably creating the final V-Sync form in channel 8. And then the final one, V-Sync, is at 60 Hz, which we know is the refresh rate of our screen. So it looks like it's all working out. If we increase the sample size and resample, we can get a wider view. Okay, so now I want to just show how the composite sync is created in order to get the TV picture going. I've hooked up the H-Sync and the V-Sync and put in some yellow wires to create the AND gate that makes the C-Sync. Here is the waveform output from those three channels. So again, the C-Sync is a combination of the 15 kHz H-Sync and the 60 Hz V-Sync. Now time to look at making the same circuit in Verilog.
Okay, so I've opened Programmer's Notepad that we used in the last episode. I have two files here, ttlchips.v, which has got the 3 logic chip code that we previously looked at in the EDA playground. And then I've got a new file called tankb.v, which is our module for our game, which is Tank B for Tank Battalion. The module is the top module. In Verilog we need a top module, so we're going to call it Tank B underscore top. This is a simulation, so it's not quite what we're going to do in the FPGA. The difference is we will have some simulation code here, which is setting out some initial variables, the state of them, and then we, instead of having a clock from the FPGA, we're going to create a clock here by saying the clock is the opposite of the clock there. So every one cycle of the simulation we'll get a negative of the clock, which creates a clock going backwards and forwards. Okay, so what we've got here is, as per the schematics, I've set it out into horizontal timer and vertical timer, and we've got each chip specified as per the chips in the schematic. One point to note is, in Verilog you're not allowed to have a number first as your label. So instead of 6A, I've always put A6. Here I've also got IC in front of that as well, so it just gives an extra name. As you can see, we can instantiate the LS107 code, which is over here. This is the 107 module. We can instantiate that, means use that any number of times. Here we're using it once, twice. We can do that by changing the label, and that is the same as a different IC number in the schematic. Now, because of the IC type, the LS107 actually has two flip-flops, JK flip-flops inside it, so therefore that's why we've got the 1 and the 2. Okay, so this we've got here is also me specifying any wires or registers that goes with the parts underneath. So in the schematics we will have, let's say, an input on outputs, and I've created wires. Now the convention is that's the chip A6, flip-flop 2 of A6, so that's that one, and that's the NQ, so the not Q of A6. So that's just how I've created it. You can do whatever you want. That's just the way that I've done it. Okay. What else to say? Here we're going to get into what I'm doing here. We're basically setting off PUR, stands for pull-up resistor, and the schematic you'll see we have pull-up resistors to connect to. That basically goes to the 5 volts through a resistor in the schematic. That can obviously be set to just 1 in Verilog, and we can't, as we'll see, we can't necessarily just set that straight away. A lot of these flip-flops get messed up if you don't change their state to start with. So hence you'll see here I do have a reset going from 1 to 0 and then back to 1 again. Same with the pull-up resistor. I'm actually going from 0 to 1 to 0 to 1 again, and that's to do with these won't work properly in the simulation if you don't do that. We can have a look at that later. Okay, so effectively I've just gone through and I've connected up the schematic, the items as per the schematic. So 6A, I've gone with a negative clock because we're drawing the clock as the first side of 7B5. So then that's negative when it goes 7B7. So that's then going negative into 6A. And then, as I say, I've just put in, made wires to go into the next one as it's on the schematic. Not much else to say really. in terms of the data inputs from the schematic, you can see we have on the first one, we've got they're all going to ground on 6B, the data ins, so that's 4 bytes of 0, and then the outputs are they're from the top downwards, so 11, 12, 13, 14, so they go H16, H8, H4, H2, and then the carry becomes B6 carry. I've just put that. H1, which is also equal to the 5A Q, is the enable P, enable T. And then on the other one, it's not all held at 0. It's not all held to ground. Pin number 5 on 6C is actually 1. So again, it's backwards. It goes 6, 5, 4, 3. So number 5 is 1 because that's held to an, it says RP3 in there, which is a pull-up resistor again. So that's horizontal timing. And then similar for your vertical timing. I've labeled H-Sync. H-Sync is the output from the 6A. So if we, good thing with this is if we highlight H-Sync, we can see where it's used. So you can see here A5 is H-Sync. Okay. And then very similar, the outputs we've got are V16, V8, V4, V2. Here at the top one, which would be V1 256, we've got NV sync. And then to create the composite sync, we've got not VSync and not HSync and not VSync equals not composite sync, as we saw on the introduction. So now we're gonna load this into Modelsim and see what it looks like. Okay, now we want to start up Modelsim. So if we go to Files, we go down to I for Intel FPGA 16. We then go to Modelsim. We click on that one. You can also pin it to the taskbar. I've got it here. Okay, so I want to go to File, New Project, project name, let's call it Tank B, and we want to say, where is it? So browse, find where I put mine. Okay, so we've got the code there, the default name, we're going to call it Tank B, and we're going to say OK. Now it's going to say, do you want to add any existing files? Don't forget we already wrote some, so yes we do, add existing files. Where are they? They're in where we've just created, so we will highlight those, press Shift and all of them, and it'll select them. And then we say OK, and then they've got them there. We want to say close, so that's done. Now we've got our files in here. What we want to do is get it running, so we want to go to compile all. So it runs it. It had a problem. It says compile tank B failed with 3 errors. TTL chips file compiled successfully. So what we can do is if we double click on the red, it gives us a window and tells us where. So it says line 9 of tank B, we've got an undefined variable. So if we go back to our thing here, you can see we've specified what this wire should be based on H64 and H32, while we don't declare that wire until below. So this is not an issue in FPGA. In FPGA this would work itself out. However, in a simulation it does seem to need to be in order. So if we take that there, we put that just one wire after that there, and we very importantly we save. Now we can go back into Modelsim, close that, compile again. There we go, this time it's happy. So we've compiled it, it's very quick because there's very little code. And then we want to go to simulate, start simulation. And then we want to find R1, so we've got a lot of stuff here. If we want to go down and find tank B, it's typically down towards the end. Here we go, tank B. You see we can't press OK by clicking on it because we have to choose the exact module, so we open it up with the plus. We always want the top module typically, unless we're looking at something specific. But right now, top module, tank B top. And there we have it, don't worry about that. Okay, so now here we want to pick out the wires we want to look at in the simulation. So we're going to pick them out from this darker blue here. This is a bit small, so I tend to press this button here, which pops it out. Make that a bit bigger. Now we're going to choose the wires we want. So I'm going to choose, we want the clock, and we're going to choose all of the ones that we were looking at in the previous breadboard. So all of the H, let's not choose that one because that's not on the schematic. We'll choose the negative version instead. Choose the pull-up resistor, choose the V's, we'll choose composite sync, we want that one, and then we want that one, and we'll choose the reset as well. Now we've chosen all of those. I was pressing the control key and choosing them. Obviously if you press shift it's going to select them all just like normal Explorer. We're going to right click, we're going to say add wave. That's going to create a new window here, which frustratingly then it goes back to this as the priority, so we need to choose it again, make it bigger, and those are our waves here. So now what I do is you can either go select all in edit, or you can click there and then shift and click at the bottom, and then we right click and I hit radix hexadecimal. So I always want to see here in hexadecimal, just personal preference for computing. Make that a bit smaller. Now there's two ways we can get this to work. We can either do one individual set of 1 picosecond, and we'd press run and that'll do the amount of time there. There we go. Or we can do this one and it'll keep on running and it'll tell us how many picoseconds it's run for there. And we stop. Okay, let's clear that. Let's put it in the right order. So let's put the clock as the top. We're just dragging and dropping. Reset. I notice power is there. Pull up resistor. So we're going to go 1, 2, 4, 8, 16, 32, 64, and then H sync, and then we want 1, 2, 4, 8, 16, 32, 256. There we go. non-HSync is up there, sorry. Where do we have non-VSync, or did we not include it? We must have missed non-VSync, so we can go back and choose non-VSync. Where was it? There we go. Add to wave. Okay, so there we go. Need to change the radix on that one, so right click, hexadecimal. Okay. So now we say here, let's try what's that? Is that a lot? Okay, there's still quite a lot there, isn't it? It's taking quite a little time to do this. Obviously, a faster computer would do it faster. Alright, so and then we can have a look at this. Let's see if we go further in. So if we look here, obviously we've got these here. Looks very similar to what we had before. Now we had the slightly curious one where it was like this, didn't we? Remember? We had the low and then that. So there were 3 segments, that's exactly the same. Then we've got this one underneath it. So we're the same there. This one was as we had it as well. So everything looks like it should. And then our HSync and VSync is looking right too. We just probably need to have a bit longer. So we will do another . Possible that the video capture that I've got going on is making it even slower. I don't typically remember it being this slow. Anyway, the important thing is that we've got this feature here that we've got on the composite sync. So we've got the dips, and then whenever we get the VSync, it obviously keeps low as well. So that's exactly what we want. So there we go. If we select here, then that stays there. It makes it a bit easier to see what bit we want to be looking at. So there you go. Now what we could do is we can go back in and have a look at if we don't set the pull-ups. Here we had to set these. We just look at these quickly. You can see I've done that to reset these. They start to go when we've done the pull-up resistor back. We go back into the code and we don't do this, so we could just get rid of the initial begin. We select that, right click, say comments, line, that'll get rid of those. We can save that. Need to go back into Modelsim, and we don't need to stop the simulation. We can just go to project, and we can recompile, compile all. That's saying that it was had a question mark there before, that it was changed. That was all happy that everything's good there. Now what we can do is just go back to our simulation. We can say restart. Okay, and then let's take 1, 0 off there, and we can do that, and you can see it's not happy at all. Basically none of the flip-flops have done anything, and that's because we didn't do that. We didn't give it a state to start with, so it doesn't know really what to do. So you need to give it that reset, and that's also true sometimes in FPGAs as well. You have to give it a reset inside the circuitry to give it a starting point. Okay, so that was it for this time. Next time we're going to look at introducing the VBlank, and then we're going to start getting some kind of picture on a breadboard and also in FPGA.